to just close down. Yeah, sorry, we went a little.
Sure. Okay, can everyone hear me fine? Yeah? Okay, all right, great. Well, I know everyone wants to finish their long day with lectures on statistics, so we'll do our best. So my name's Kyle Crammer. I'm a professor at New York University. I work on the Atlas experiment. I try as much as possible to have good working relationships with my theorist colleagues and spend a lot of time trying to take the experimental results that we have and understand the theories that we're after and try to make the connection between them and the testing of them as clean as possible. And so a lot of times that's done in the language of statistics. And I'd like, for me, it's a bit of an art in the end if, the more direct the link between the theory and, what it's predicting in the data and that connection of inference, the cleaner that is and the more direct that is, the happier that I am. And a lot of times you see sometimes data analysis that goes through a lot of different intermediate steps and the theory gets rewritten in lots of different ways. And sometimes it's hard to kind of keep the thread between, the quantum field theory that you're using to make a prediction and if you've actually excluded that theory or not based on what the measurements are doing. So that's basically the theme of, the course is to talk about statistics sort of in the context of high energy physics. And I don't know. Please feel free to ask. I'm still a little bit up in the air about exactly what to cover. So I've given a lot of statistics academic training lectures. A lot of times it's aimed more towards an experimental crowd, and sometimes it's a mixture of experimental and theory. Usually, what I do is I start off with just some very basic definitions of things so that we're on the same page in terms of terminology. And then I go through, I talk about estimators, which is basically measurements, like what's the best fit value of some parameter of your theory or something like that. And then I talk about hypothesis testing, and I talk about like confidence intervals or limits and exclusion contours and how you make those. But there are some other topics that I think people might be interested in. There's something that's coming up, especially in the context of this 750 GeV excess, which is called the look elsewhere effect. That comes up in lots of places. It's kind of a subtle issue, so we could talk about that. There are some other things that are kind of pretty that have to do with, to me, it's sort of the language in which I like to sort of think about phenomenology at a very high level, which is, which goes through this kind of language of a statistical model that's describing what you expect to see, and then I can recast it into a language of differential geometry. So there's a whole topic of information geometry, which is a really kind of nice way to think about phenomenology. So I could talk about that for a little bit. So if people have kind of requests or something, please just tell me in the talks, and I will try to spend more time kind of talking about some of statistical ideas in a more like mathematically refined way than a lot of times it's talking to lower level or experimentalist colleagues that don't have as strong of a math background as you do. So before I get started, just since we were that you ended with talking about those PMSSM scans and interpretations and things like that, one pet project that I've had going for several years is this thing called Recast, which was basically been an idea but is slowly coming into reality. And I just thought I would mention it here. So this website, the whole point of this is that is for sort of if you have a theory in mind and it was never tested explicitly by one of the experiments and you want to know if your theory has been ruled out by one of the searches that's been performed. So the PMSSM scan was not a new set of searches. The searches were already there. It was reinterpreting those searches in the context of that theory. And so that idea, we sort of dubbed that recasting, okay? You're reinterpreting an existing search. And we've set up this website to basically try to formalize that and organize those requests from the theoretical community. And the website just got a facelift yesterday. but it's here, and you can see basically the idea is you have lists of analyses from the experiments. You could go to one of these analyses, and then if you want, you could add a request to it and say, here's my new theory, and you could upload like a MadGraph model file or something like that, and it's a request to the experiments to actually process these things. And the hard work has been trying to actually make it so the experimental analyses can be behind all of this and work. But that's we now have some examples, and in this Atlas PMS SimScan that was shown, some of those use this system internally. So that was so it's becoming real. We can take real Atlas and CMS analyses written by the experimentalists and integrate it into this whole thing. So anyway, so that will hopefully become more of a real tool sometime soon. Okay, so here are my slides. I uploaded these slides onto the wiki page, and then I also uploaded some lecture notes so that are on the archive. There's the archive number there. So this is the lecture will follow a lot of the same kinds of things, and I'll try to align the same nomenclature and etc. with those notes. It's a kind of a living document, and my goal was that it would be at one point something like the SUSY primer, but for statistics and high energy physics. But there's still a lot to add to it. Okay, so then to get started, I kind of already said this a little bit, but the sort of main topics for statistics, as I see it, are it's we're trying to quantify our knowledge from the experiments that we've done, and cast it in a way that's relevant for the theories. It's the big questions that we'll be addressing basically are, for instance, how do you make a discovery? Like, what is the statistical statement around a discovery? Measurements, and when you want to exclude like parameter space of a theory. There's also just the issue of how do you get the most out of the data. Okay, there's like silly ways to do it, and then there's more advanced ways to do it. And what I'll show is that there are actually some upper limits for, formal upper limits for how well you can do, like how much information you can squeeze out of the theories. Out of the data. There's a big topic, which is basically how do you incorporate uncertainties. That's, as an experimentalist, is like one of the most important things, because we have all these complicated experiments, and we need to make all of that show. As a theorist, maybe you don't really care, but if you ever, if you want to ask probing, penetrating questions about do I actually trust that analysis, you're probably going to be caring mainly about the uncertainties, and it's good to have a framework in which to understand uncertainties and things like that. So I think it still makes sense to spend some time on that. And then there's another part which we don't, is not usually in most of the other lectures that you see about statistics and high energy physics, which is about how do you make decisions. Okay, and so really that's it's a decision theory. Okay, there's statistical decision theory, and it's kind of like a level above normal statistics. And but I think that that's also a very important thing to be thinking about, because like, what are the big questions right now? I mean, one is, what are you going to spend your time doing? Right? Am I going to work on this topic or that topic? Right? That's a decision about how you're going to spend your time, and hopefully you want to be able to be equipped to make decisions like that in a rational way by looking at the evidence that's there and then taking into account like your, all the information that you have. And maybe you're not going to do it numerically, quantitatively, like multiply a bunch of numbers together, but it's a conceptual framework to work within, which I think is useful. The other one is, later Nima will be talking about the future of high energy physics. I'm sure we'll talk about 100 TeV colliders, and there are lots, you don't want to be thinking about budgets at this point, but we are working in a world with limited budgets, right? And we need, as a field, need to figure out which of these things to do next. Neutrinos, 100 TeV colliders, a whole bunch of small experiments, high luminosity LHC. And it's very nice to be able to think about those questions in a decision theoretic way. And I'll try to, sort of give some formalism to think about it that way. Okay, we're clearly not going to get through all of that. So, we can't get through all sorts of these things in gory detail. So we'll have to kind of adapt as we go along. And so please ask questions and et cetera, et cetera. Yeah. Should in the middle? Yeah, sorry. I don't. Yeah, I realized that. Well, I was thinking at first, this table was here, so I was thinking about and that projector doesn't work. We could put it in the middle, and I was just going to use the boards too, so I just walk it back and forth, but that's doable. No, I was going to do kind of a mixture of the two, but there's a sort of a fair amount on the slide. Should we just switch it real quick? Yeah. Okay. Yeah, thank you for saying. I was noticing too that I'm over there and everyone over there is like, I can't see anything. Okay. Sorry. Okay. All right. I'll continue while this gets switched. So, okay. So the first thing that I wanted to do is just define some terms. Okay. A lot of these words are words that you have heard, unless you have some special talent that most people I have run into don't have. It's very easy to get all of these confused, partially because they're roughly synonyms in English, and in different languages there's not even a different word for them. So like probability and likelihood, for instance, they sound very similar to each other, but they as you'll see later, they're quite different, and the way that I'm going to try to talk about it is in terms of the way that we think about quantum field theory. Talk about transformation properties and things like that. So I'll talk like some things are invariant under some kinds of operations and some things aren't. So let's go through them real quick. See, I'm gonna do this. That is no longer plugged in. Sorry. Okay, that is. Okay, so sorry. We would have gotten this set up a little bit earlier, but okay, so the first thing that I'm going to be talking about are, so I'll say random variables or observables, and by that I mean the things that you actually measure in your, not measure at the level of like what's measure the Higgs mass, but like voltages, currents, energies of particles, angles of particles, things that you're observing in your experiment. Okay, so I'm going to call those. So that's X, and what's going to be important here really is that I use Roman script for that. Okay, and then we'll talk about probability density functions and probability mass functions. The only difference there is if something is continuous or discrete, right? If you have something that's discrete, like 1 event, 2 events, 3 events, then you have a probability for each of those outcomes. And if you have a continuous variable, then you have a probability density. Okay, and so I'll call those P of X, and in a lot of the notes it's written F of X, so I'll go back and forth a little bit. And then we'll talk about a parametrized family of PDFs, and generically I'll call this thing a statistical model. Okay, so that's P of X given alpha. Okay, so if I tell you the parameter alpha, then I know what the distribution of X is, and if I change the alpha, I get a different distribution of X, right? Now and then I have the actual parameter itself, alpha. Now I'm going to, as much as possible in these notes, and something I just kind of try to recommend is to use Greek letters for the parameters and Roman letters for observable things. And the reason for that is that especially when we start talking about things that have to do with Bayesian, like Bayes' theorem and Bayesian analysis, there's a probability inversion that happens, and where you get something that looks like probability of alpha given X. And humans make that inversion all the time. It's like the most common mistake, that we do all the time. And so if you have different, convention for how you write it down, you can see manifestly if it's a Bayesian or a frequentist statement. It's sort of like upper and lower indices for a Lorentz, Lorentz indices. So it makes a lot of things manifestly obvious in the notation. So we're going to stick with that. Then there's the idea of the likelihood function, likelihood, L of alpha, my parameters. And then we'll also talk about the estimate of a parameter. Okay, so usually we think about the parameters as it's some knob I can turn in my theory. I don't know what the true value is, but I can try to estimate it and based on some data. And so that's alpha hat of X. Okay, that's the typical notation. All right, so far so good? Okay, great. So probability, probability is simple for discrete things. You're just saying it. One thing I'll go ahead and say here is that, the way later we'll talk about different definitions of probability, which is a little bit surprising maybe, but the way that, the intuitive starting point is to think of it as a limit of the frequency of some type of occurrence. So for instance, I want to know the probability of threes. I roll dice a bunch of times, and the limit of the number of rolls that got a 3 over the total number of trials is the definition of what I mean by probability, okay? I know that sounds like too stupid to say, but that's not always going to be the case, okay? Another point here is that it's a limit. It doesn't mean that you actually have to get to infinity. You just need the limit to converge, right? So there are some people that try to make ridiculous arguments about this notion of probability not making sense because you can never do something an infinite number of times. But if you know how to take limits, then you know that doesn't really matter. Okay, PDFs. So again, PDFs are not probabilities. So if here's a Gaussian curve for some variable x, the height of this curve is not a probability, right? It's a probability density. It has units that, that are 1 over whatever the units of x are, it's what do I want to say here? And of course, the height of this can be bigger than 1, right? If this is a really narrow range, then the height of that is bigger than 1, so that the integral under the thing is 1. Okay, so now there's also something called the cumulative density function, where you just integrate that thing. It's very clear in one dimension, and higher dimensions it becomes a little bit more ambiguous. But the thing that I would say here is that this relationship between a cumulative density function and a probability density function are just like a total cross-section and a differential cross-section, right? So if you want, you can think of I divide by the total cross-section, and then I have the differential cross-section, and that is a probability density function, right? And also, if you go back to how you define cross-sections, the very beginning was that you're calculating probabilities of scatterings, right? The starting point is, ins and outs, and then you take a probability and you rewrite it as, phase space and blah, blah, and cross-sections to be in some Lorentz invariant form. But, the starting point, the real core first principles thing was a probability to start with. Histograms, I think everyone knows what a histogram is. Not much to say here. The main thing that's worth mentioning is that if I have a bunch of example data that were, you say, drawn from a distribution, and I want to approximate that distribution, I can just make a histogram. It's the easiest way to do it. One thing that happens a lot of times, though, is that people make a kind of conceptual mistake of thinking that the histogram really is the probability density function. It's an estimate of the probability density function. It's not exactly right. I mean, you can see the histogram doesn't look exactly like the perfect curve, right? And that becomes important sometimes later on. That people make some kind of logical mistakes, but we'll get to that later. Okay, now I talked about a parametrized family of models. So let me give 2 examples here. So the first one, so these are 2 very important distributions. One is the Poisson distribution, and one is a Gaussian distribution. Okay, so the important, I just realized, is there any pointer anywhere? Is it up here, or? I can also do this or something. No, I can't actually. Or a stick. Oh yeah. I could jump, but it would be embarrassing. Okay, thank you. Okay, right. So again, we're talking about this f of x given alpha, and think about it for a little bit. There's a fair amount of structure that's going on in that. I mean, you have a whole parameter space of, say, a theory, and x might also be high dimensional. It might be the whole phase space of what a scattering process looks like, right? So as you move around the parameters of your theory, the whole phase space distribution is changing. Now in this example, the Poisson, one thing that's nice about it is that the parameter mu is continuous. I can talk about an expectation of 2.3 events happening within the year that some dark matter detection direct detection experiment was running, right? 2.3 is an expectation for mu, makes sense, but n is obviously going to be discrete. Okay. Another quick thing, since Poissons happen a lot, is a quick mnemonic about remembering this formula, is that if you can just remember kind of e to the minus mu, okay, so which is the first part, which is also important if you observe 0 events. If n is 0, then this goes away, and you just have e to the minus mu. So if you can remember that as a starting point, then you know that the whole thing needs to be normalized to unity, right? So you're going to have e to the minus mu times e to the mu, right? And then you do a Taylor expansion of e to the mu, and each of those are the terms of the Taylor expansion, right? And if you sum this up from n equals 0 to infinity, you get 1. So, okay, mnemonic for the Poisson. Okay, now the Gaussian you see all the time. Here's the formula for the Gaussian, nothing interesting there. Now here, this is the part that is, it's going to sound super easy, but is just, it's very, it's the part that people mess up on a lot. So let's try to just say it very clearly. So the likelihood function is the same function. It's the same function as the probability model, but where you keep the data fixed and you think of it as a function of the parameter. Okay, so the value of it is the same. So you can see why it's so easy to make mistakes later, but it's going to have a lot of different properties than the PDF does. Okay, so basically you have this statistical model, and you can either fix mu and think of n, and then you have a probability, mass or density function, or you can hold n fixed and think of it as a function of mu, and then it's the likelihood function. Okay, so now of course if you take, so I'll draw over here. So if I have a Poisson distribution, so here's n, and this is say 0, 1, 2, 3, 4, 5. You might have a distribution. It's it's discrete, so it's going to look something like that, right? And then if I actually observed, so let's say I actually observed 3 events, then I have a different thing, which is this likelihood function as a function of mu. Okay, so if I plot the likelihood as a function of mu, it's going to go up. It's continuous. Okay, that's not going to look exactly like that, but it's going to go up. It's going to come down, and it's going to have a peak at 3. And it looks a lot like a probability density, right? So that's why it's so tricky. But the integral under this thing is not 1. Okay, and other things that I'll mention in a little bit. And so for reasons that are kind of silly, I would advocate instead of plotting the likelihood of mu, always plot the minus log likelihood of mu, right? In which case, this thing is going to go, something like that, right? And then this curve never looks like a PDF. You'll never get that. You'll never make that mistake. And then there are also going to be reasons later on why the log likelihood is really like a very convenient thing to work with. Okay, so this one is L, and this is minus log L. Okay. So I know it seems like I'm treating you like children for all of these kinds of advice, but it's still, I think it is helpful. So here's this plot, and what's nice about the Poisson example is that it's continuous, so it's maximally different from the probability mass function. Okay, so basically said that. Okay, so let's talk a little bit about transformation properties of these things. So let's say at first here's some little dummy code. It doesn't matter. All it's doing is imagine it's a spinner, and I flick a spinner that spins around between 0 and 2 pi, and it stops at some point, and the distribution of that angle is uniform. Okay, so I have a nice uniform histogram of that distribution, and let's call that variable x. That goes between 0 and 2 pi. And now, what happens if I make a histogram of cosine of x? Is it going to be also uniform since it's just a random angle between -1 and 1? Right. It's not. It looks like that. Okay. It picks up peaks, and so the distribution, the PDF, is changing when you change variables from x to cosine of x. Okay. So here's a kind of quick example of here's x. There's my cosine of x, and what's happening is you can imagine uniformly scanning here. But whenever the x is close to -1 or 1, all the probability kind of piles up, right, at 1 and -1. So that's it's sort of like when you look at a nebula or something and you see this ring, the shell around it, you're like, why is there a ring that happens to be pointing at me, right? It's a shell, but you're just looking through the edges and you're picking up probabilities. So there's a Jacobian factor that you see, and if you remember doing 2-body and 3-body phase space, right, you write out the Lorentz invariant phase space with a bunch of delta functions, and all you do is chug on that and calculate a bunch of Jacobian factors to figure out what phase space looks like. It's exactly the same thing. One thing that's interesting about phase space is that I could have there is, in some sense, a natural measure, probability measure for phase space, right? Which is that it's like uniform in the momenta, right? And that's before you put the delta functions. You could have thought, the Jacobian tells you how to make a transformation from one set of variables to another, but it doesn't tell you what the original distribution is. And so the statement of phase space really is that it's uniform in the momenta at first, and then you pick up all the Jacobian factors that turn it into something non-trivial later. I don't know if I don't really need to go through calculating the Jacobian, but basically all you say is that the probability that x is between xa and xb is going to be the same that y is between whatever its transform value is, y of x and y of xa and y of xb. So you just equate these two probabilities, and then the equation on the right, you take this and you just rewrite it using calculus to change variables back to x. And then you identify that the distribution g for the variable y must be equal, times this Jacobian factor must be equal to the original f of x here, because you see that the integrals have exactly the same limits and everything, so the integrands must be equal. Okay, so that Jacobian factor, so the fact that when you change variables of the observable, the distributions change. Whenever you talk about any probability density function, you have these Jacobian factors that are important. That is not the case when you talk about the likelihood. I stole this slide from Bob Cousins. It's a bit very bold fonts, but the main point is that if I think about the likelihood function, let's say, let me see if I can think of a good example off the fly. Is that if I changed, mu here, for instance, was the number of expected events, right? What if instead I turned that into something that was proportional to a coupling constant? Then the number of, if I thought of the number of events in terms of some coupling constant and some factors, right? It would probably be the coupling constant squared that would show up, right? So I could think of the likelihood in terms of the coupling constant squared, right? And if I find the same, whatever the value of the coupling constant is that gives me 3 events, it's the same distribution. It's the same prediction, right? So the value of the likelihood is going to be exactly the same. We're just going to be plotting it with respect to a different variable. So the value of the likelihood is totally invariant to reparametrizing the theory. Okay, and that's very important. Okay, so that's why these transformation properties are very different. However, the other thing here is that if I change the if I change the observable quantity where I pick up this Jacobian, the value of the likelihood is going to change. But if I make likelihood ratios, that Jacobian is going to cancel. Okay, so for instance, in this plot, this is the minus log likelihood curve, right? If I changed, from, the variable n to it's not a good example for a discrete quantity. If this was if I thought of a continuous quantity where I pick up, okay, this is a bad example. Okay, well, we can do it really quickly. So let's see. I mean, we could do that. The example that I showed before, which was like, uniform between 0 and 2 pi, and then another distribution that looked like this, which was between -1 and 1 for cosine of x, right? If I made that transformation to of the data, I would actually have some particular data points here, right? And then they're going to transform into something else over here. And then let's say I had some way of parametrizing what I thought the distribution looked like here. Okay, let's say I thought it looked like, I'll just come up with an example quickly. Let's say that let's say that, okay, something really simple. Let's say that I thought it was A plus bx or something like that, right? For the so this is my variable x, and I thought the distribution. So this is p of x given the I should call them alphas and betas. Sorry, alpha and beta, given my parameters alpha and beta. And I guess really there's a normalization condition, so there's really only one free parameter in here. So let's just call it alpha. Then if I made a likely, so I could, does the distribution look like this or something? When I transform to here, I'm going to get different kinds of distributions, right? over here. And when I make the likelihood function for alpha, so let me plot minus log likelihood as a function of that parameter alpha. If I took the value of the likelihood from this plot, that curve might look like this. And if I took the likelihood from this plot, it's going to be changed by some Jacobian factor. Okay, so it's going to have it's going to be a different curve. So this would be from this plot, and this would be from this plot. Okay, so the actual value of the log likelihood is going to shift because of the Jacobian factors. But the important thing is that the likelihood ratio between, like the minimum is still going to be this happening at the same point. And if I look at between this point, I'll call it alpha hat, and then some other point over here, alpha 1. So if I look at the likelihood ratio between these 2 points, so it's going to be this difference. Okay, so if I have the likelihood ratio of alpha hat over alpha 1 that I called it, right? And then if I make it a log, minus log likelihood of this likelihood ratio, which is what I'm plotting, then this just turns into a difference of the minus logs, right? So it's just the difference between here and here. Okay, so that gap has to be the same as the gap over here. Okay, so the Jacobian factors are going to cancel. Okay, so so that's why, and that's one of the reasons why when you see plots like this all the time, and maybe that the quick way to make an exclusion contour in a plot is you make the plot of the log likelihood, or like a chi-square. You find the best fit point, and then you go up by some amount. Okay, and that's part. I mean, we haven't justified why that's an interesting thing, but at least one thing I know is that it's invariant to reparameterizing the observable. This approach. Yeah. You're right. This would be sort of for a fixed in here. Yeah, yeah. Right. Right. Oh, there's nothing wrong with it. I mean, it's all the same information, right? I could plot the likelihood function, and it would come up, and it would peak, and then it would go down. Or I can plot the minus log likelihood, and it's it's just nothing is different. It's just the peak of the likelihood is going to be the minimum of the minus log likelihood. There's going to be lots of reasons why the log likelihood is nice. Another thing is that if you plot something like this, you're never going to look at it and think it's a probability. It's kind of a joking way, but it's also not, it's not a bad reason, I think. Yes?
So when we say that is the likelihood function, is there an implicit notion of the prior?
Yeah, that's great. So you tell me. So where is the prior here?
You're assuming a flat prior on that
parameterization. I don't know. Am I?
Because by Bayes' theorem, I seem to have inverted x given alpha to alpha given x.
Yes. So that's kind of exactly the point. So we'll get there, but maybe I'll just go ahead and say it now. Is that if I wanted to? Oh, that's not going to work. So if this is mu, and I plotted something that looked like this, and I wanted to interpret, the height of this thing as a probability of mu given x, then so if I wanted to think of this as p of mu given x, then there's like some, the area under this curve would need to be 1, right? And we know that the thing that I'm plotting, the area under the curve, is not 1. And also, so the thing that I'm plotting is not that, okay? So I don't know, maybe we should just, I was going to get to Bayes' theorem in just a little bit. So maybe I'll come back to this slide in just a second. Yeah, okay. All right. So we talked about these transformation properties. This is just another little kind of corollary to that, which is if I choose a particular way of transforming the variable x into a new variable y, and it's this transformation. So I have my variable x, and I also think I know what the distribution of x looks like. So that's f of x. If I have those two pieces, I can. This is a particular transformation y of x, right? Where I just do the running integral from minus infinity to the value of x. This cumulative distribution. So if I do that, I don't think about this in terms of probabilities. Just think of it as a variable change. Okay. If I do that and I calculate this Jacobian factor, I need dy by dx. And if I take the derivative of this, the integrals and derivatives just kill each other, and the Jacobian factor is f of x. Okay, and then I'm going to divide that out, and so the distribution for y, the variable y, is just going to be 1. Okay, so what it's saying is there's this particular way of transforming some complicated distribution into a new variable y will always give me a uniform distribution between 0 and 1. Okay, so it's a way of standardizing any kind of weird complicated distribution that you want. And that becomes important, especially when we start talking about Bayes' theorem. So maybe I'll start to flesh this out. So if I wanted to plot this probability of mu given x, I need Bayes' theorem for that. And the Bayes' theorem is going to say that p of mu given x is equal to p of x given mu times a prior on mu, and then times some normalization constant that makes it all be 1, but that normalization constant turns out to be whatever p of x. Okay. Now, so this part right here, if x is fixed, this term, I mean, x is sitting in front, but it's fixed. So this is a function of mu, and this is the likelihood, right? This part right here is the likelihood. And this part right here is called the prior. And this piece right here is then called the posterior. Okay. Okay, so when we plot the likelihood, if I did have a uniform prior, and I multiplied it by the likelihood, it's not changing the shape at all. All it's doing is changing the normalization so that that it integrates to 1, and I can think of it as a probability, right? That's unfortunately the source of all of the confusion about Bayes and frequentist, is that people usually equate these two things as being the same, and there's an implicit 1 here that no one ever realizes, which is playing the role of a prior, and people don't recognize it as an assumption because it's just 1 and you don't see it anywhere, right? But these two things are definitely not equal to each other until you put in this prior and normalization, okay? And so when you plot the likelihood, a lot of people want to say, oh, that's the same as just a uniform prior. But it's really not, okay? And one of the main reasons is that if I wanted to change variables from mu to, I don't know, call it phi of mu, some new variable, then the posterior would pick up a Jacobian factor. But the likelihood is totally invariant under this kind of change. Okay, so they're really different. Okay, and so that kind of comes back to this other point that's here, is that this probability integral transform, nice trick, it's useful. It's particularly handy if you're doing Monte Carlo, okay, if you need to generate things out of a complicated distribution. If you transform the distribution in this way, then all you have to do is sample from uniformly between 0 and 1, and then take the inverse of that function, and you're sampling that distribution. So if you think about, for any of you that are involved in Monte Carlo generators, you have phase spaces all complicated. So what these things like Vegas and all these adaptive mesh blah 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 are doing, they're basically trying to figure out this kind of transform, to put it into something that's uniformly sampled. But this point is the thing that I wanted to focus here, is that the specification of a Bayesian prior p of mu, the thing I called pi of mu over there, for some parameter mu, is equivalent to the choice of the metric in which the PDF is uniform. Okay, that's my mu to phi of mu, right? I can always find, either you tell me this thing is, it's that I have a uniform prior in mu, and I go to a different variable and it's not uniform anymore, or you tell me that uniform in phi, and I go back the other way and I inherit what its non-trivial structure is in mu. Yeah.
So just to understand what this probability is about. So it tells you that that's the probability of your model having some parameters set mu. Is that right?
That's right. That's right.
So like that will almost never be one. It'll just be some random.
Yeah, so that's a whole separate set of discussion, which I was going to get to at some point, but we can talk about it now. Is that we can think about the justification of these pieces, right? So this piece right here is coming from the theory, right? I mean, that's what we do when you do quantum field theory, right? You have coupling constants, Lagrangians, higher dimensional operators, whatever you want. You know how to compute, and you get a distribution for some observable, right? So this is what we do in standard physics, right? Now, what's interesting is we were talking about the MSSM earlier. Like one of the parameters in the MSSM is tangent beta, okay, like the ratio of the Higgs webs, right? Well, what if I chose to parameterize the theory instead of tangent beta in terms of beta, right? It's the same theory. I'm just writing it down a different way, right? If aliens came from Mars and said like, oh, well, we also believe in supersymmetry, but we like to call it, then it's going to be, they're going to have a different prior. So but they hopefully would agree on quantum field theory and all that stuff. So this part is physics, but where do we get a prior for the parameters of the theory, right? That is not coming from any kind of calculation. Okay, well maybe it is if you do anthropics or something. Seriously, but if you don't have something like that, you just have a normal theory, like even the standard model with the Higgs mass parameter. Like you can say like, well, I don't think it can be too heavy because the theory, becomes unstable, and it can't be too light because of whatever. But within the ranges, you have no reason to prefer any value than any other value, right? So this is why a lot of particle physicists really don't like putting priors on parameters and sort of don't like doing Bayesian analysis. Okay, and what's odd is that we're really one of the only fields that isn't like on this Bayesian bandwagon, because lots of people do Bayesian analysis, but a lot of times that has to do with, for instance, that prior is based on something like, if you're talking about diseases, like you take this is like mu could be like I have Zika or I don't have Zika, right? And X is like the result of my blood work, right? And then based on that, I'm going to say like, do I have Zika? What's the probability I have Zika or not? But I also have prevalence of how many people have Zika in the world, right? So that is based on actual information in that case. That prior is based on something, and the analog to that would be something like the multiverse and scanning. But if you don't have that, then where does it come from? And I guess it also goes back to I'm jumping, like maybe I'll just. Okay, yeah. Well, okay, it was actually going to be the next part. Yeah, here's a. What's that? The question is, in particle physics, do you ever need a prior? So if you want to ever answer a question of this form, what is the probability of my parameter given the data? Yes. You just can't get around it. I don't know. You might. So people do it all the time. In our typical conversation, this is usually how we discuss it. And so but that's all, it's just kind of crazy because it's how we talk about it all the time. It has to be like this. This is the physics. So we're just always sticking in a factor of 1 here based on however someone told you to parameterize your theory. I don't know. So it's an important issue. If you have some justification, you can do it. Or let me. So I have a few slides, and then we can maybe come back to the discussion. So yeah.
How do you get P of X?
Right. So one thing that you can, it is a weird quantity. I mean, one thing that it has to be is that it just needs to be the normalization constant that happens here. But you can also rewrite this thing as thinking of it as the probability of X given mu, and you integrate over all the possibilities for mu. So there's a few ways to calculate that thing. And this term in some communities is called the evidence. which I personally think is kind of, I don't know, all these words are weird words, but they're highly overloaded, terms. But so you might think that this is somewhat surprising. Like, we're talking about probabilities and statistics. Shouldn't this all be like, it's math? How is how is there any freedom here? But if you go back to the very beginning of everything, it's it is math, and it's based on axioms, and they're based on the Kolmogorov axioms, and there's just these 3 ones, and basically all of probability and statistics follows from this. But what's interesting is that you just need a probability measure, P of E, that satisfies these axioms, and then you're off to the races. No one told you where you got P of E from, okay? Like how you assign probabilities to the elements. So one way of doing it is the thing that I was mentioning before, where you have the probability is defined as the limit of long-term frequencies, okay? That will satisfy the axioms. Okay, and that is the kind of classical frequentist definition of probability. But there's another version of probability that will also satisfy the axioms, which is a subjective degree of belief. Okay, which is kind of funny because it's totally subjective, but you can assess it. Like if we make a bunch of bets, and I take all your betting odds for different possibilities, I can slowly work out in a quantitative way what your degree of belief is for all the different options. And if you are rational and consistent, then it will satisfy the axioms. Probably not surprising. Most humans betting is not consistent and is not going to satisfy the axioms. Okay, so you can, and sort of taking advantage of that is sometimes called a Dutch book. Not my word. Yes. I think that, I think certainly, that notion of like a thermodynamic picture where you're sampling all of the states is very like begging for a frequentist interpretation of probability. In terms of would you derive it that way, I think that you don't need thermodynamics to talk about this. But when you look at thermodynamics and statistical mechanics, usually they're starting with all these probabilities at the beginning. And they're thinking about how often, in the limit of long term, you have lots of sort of trials to visit all the states, and then you have how often do you actually, how frequently do you actually visit those states? So I think it's the same notion of probability. And also, at least my interpretation of kind of quantum mechanics kinds of things, when I do like, some inner product squared and I get a number like a half, usually like the Stern-Gerlach or something, I'm thinking I have a beam of a whole bunch of electrons and I run them through the thing, and 50% of them are going to come out one way and 50% are going to come the other way. And that's what I measure, right? So it's like okay. Anyways.
Sorry, quick question before you move on.
Yeah.
The way you form a degree of belief if you're a sensible person is by running trials. So isn't it exactly the same thing in the end of the day as a frequentist?
But to run the trials, you would need to know, like say you wanted to run trials of does the Higgs exist or not? Or is 750 real or not? How are you going to do that?
I see.
You basically are assuming it, and you're going to code it up, and then you're going to run trials. But like all you did was like take what you were thinking and put it into your code, right? Yeah. So if you can find a way to talk about the probabilities in a way where everyone agrees on the simulation, then it's a it's a prior, but it's also it might be some things that are priors are still obey the frequentist definition of probability. So one thing here is Bayes' theorem is a theorem. It's not that it's not true. Okay, it's not that Bayesians and frequentists are arguing about if Bayes' theorem is true. It's a theorem. The situation for Bayes' theorem, for frequentists, is that they would say if mu here is like the mass of the Higgs, and you wanted to know like what's the probability for the probability density for the mass of the Higgs given the LHC data, they would say you can't calculate that because you would need a probability for the mass of the Higgs, and that is not defined in any sensible way as a limit of something that I can identify. So this is just not defined. So I can't write it down. So I can't carry out the calculus, right? So it's not that you're saying that this theorem is false. It's just this thing doesn't exist.
So if you have the luxury to be a frequentist, you should always be a frequentist?
So it's a luxury and it's not. The problem, so I guess, that what do we? The question is, what do you want to do at the end of the day, right? As a frequentist, you're always going to be constrained to making statements that are of the form probability of data given theory. And so if you want to say, after running the LHC, what's the probability that the Higgs is real, you just can't make that statement. So it's annoying, right? So you end up having to make sometimes awkward statements. So the statement of discovery, for instance, is like, if the Higgs was not there, the probability of getting data this extreme or greater was a very small number, therefore the Higgs, right? So, it's an awkward kind of statement, and and basically all of the frequentist like discovery statements they're always conditional statements. And in the Bayesian way, you get to make a nice declarative statement. The probability of the Higgs given the data is blah, right? It's a nice, beautiful, and that's why journalists want it. That's why, it's kind of nice Donald Trump language, you're straight to the point. But the thing that if you don't, but you have to come with a strong prior, right? If you don't want to do it, you always have to make these slightly more awkward statements. And so that's one reason why a lot of people really don't like frequentism, is because they don't feel like it's sort of answering the question you want to answer. But when I talk about it later, so that's why I also wanted to bring in decisions and things like that, is because we'll talk about how do I go about my life as a frequentist versus a Bayesian, and like how do I make decisions and do sorts of things, with and without that prior. And I think it becomes all of this discussion becomes a lot more clear in this decision-making context than it does here, I think. Okay, so so there's this funny one to remember, that probability of data and theory is not theory and data. Okay, but and then there's also this one, which is a quick. It's pretty easy to remember, but this is also just a very nice graphical proof of Bayes' theorem, is that you imagine like a dartboard, if you want, the square is like a dartboard, and you're throwing darts at it, and they're filling the square uniformly, right? And if I wanted to ask, like, what's the probability that I hit target A, it's the area of that vertical ellipse over the total area. What's the probability I hit target B? It's that one. What's the probability I hit A given that I hit B, right? That means I know I hit B, and now I just want to know what's the probability I also hit A, right? So that's this kind of thing. Probability of B given A is just the other version. Probability of A and B means I hit A and B, and somewhere in the, out of all the dartboard possibilities. And then based on those things, you can put together and see that these two these two products are equal, and then you just move one to the other side and you have Bayes' theorem. Okay, yes? Yeah. Yeah, I don't know if I would use bias has a kind of precise definition in statistics, and it also has this very heavily overloaded, pejorative type of connotation when you talk about it, right? So it definitely changes that. It's clear. Like if I change pi of mu to some other thing, it's exactly linear in that, right? So absolutely, if you change the prior, your posterior is going to change. Yeah. Yeah. So so it's so in Bayes' theorem, you come with this. Everything is you assume a prior, and then you carry out. If someone else comes with a different prior, they reach a different conclusion, and there's no like who's right. They're both right with respect to their priors, right?
But in the asymptotic future, your prior shouldn't matter, right? At finite times, yes.
Yeah, finite times are like how much data. So if the likelihood, like if let's say that my prior, pi of mu, it doesn't have to be flat, but like say it, I'll just draw it flat here now, and I have a posterior. Sorry, let's call this, well, whatever. This is the likelihood / posterior, right? So but if I had a likelihood that was really sharply peaked, right, which is usually, hopefully what happens if you have a whole lot of data, your likelihood gets very, very sharply peaked, then the only thing that matters for your prior is kind of what's going on in this neighborhood. So if I had a different prior that looked like, like that, it's not really going to matter because they're basically the same in that spot. But if your problem fits into that category, yes, but not all things have this asymptotic property that things become, there are exceptions to that. Yeah. Yes. Yeah. Yes. So yeah. So that thing, that's called a Bayes factor. The ratio of the posterior is called a Bayes factor. And in a simple case where you don't have any, where you just have a prior on the parameter that you care about, it cancels, and it's all good. But if you have other parameters like nuisance parameters that you don't care about, I'll talk about them later. But like, say this is like the Higgs mass, and there's some other parameters that are like, if the LHC, if the Atlas experiment properly calibrated their calorimeter or something like that, and all these other kinds of things that you might have, you have to get rid of those, and so that usually involves integrating, and then you have a ratio of integrals, and the things don't cancel anymore. So they can, yeah. So yeah, so I can try to find some time to talk more about those, but yeah, absolutely, yes. Oh, you're asking, is it the case that rational Bayesian agents? Yeah. So, okay, we're really kind of getting into, this is all great discussion, but the some of which I don't have like something on hand for. So there are a lot of like claims that basically all rational Bayesians will always going to agree on everything, so it doesn't really matter. And usually the examples that come up are to me, they're not very satisfying. They look like, I don't know, either some kind of people appealing to some very mathematical argument that you don't know the rest of the story to, or it's somehow it's just some statement that rational agents are going to do something. If we just think about high energy physics, and we think about probability that SUSY exists or doesn't, like I consider all of my theoretical colleagues to be reasonable people. They all basically know about what the information in the state is, but there are radically different pictures going on. There is a big result, which is, what is it called? It's I should know, Almonds Theorem or something. Yeah. So if you read that, and a lot of people point to. Yeah. So a lot of people point at that, which is interesting. It's basically saying if you have common knowledge. And you might start in different places with your priors, and then and you have common knowledge, and you're able to kind of talk to each other. And as data comes in, then everyone will converge on the same thing. And that's true if people are like all rational, etc. But there are a couple. So I've almost written something about this. So if you go and you follow through that theorem, there are two very big important requirements for that theorem to go through, which are, I think, the points where basically that for me make it not at all satisfying. So when I come back next time, I'll try to address that, because a lot of people point to that theorem as like, that's why you don't have to care if we're all rational. But I think it's really not, I don't know. Okay. But it is, the theorem is true. It's just, again, it's like, it's based on some requirements. Okay, so we did Bayes' theorem here. Okay, so I need to see how I am on time to. Yeah, we started late. What's that? 15. Okay. All right. So we talked about this. There was a question a little bit ago about should you be frequentist if you can or something. Though I don't have that strong of an opinion, but the one thing that I will say is that I have found in my personal experience that if you allow yourself to be Bayesian, it's very easy to just you have some information, you have some guess, it's based on previous measurements and things like that, and you just kind of quickly slap up a prior as a quick summary of all that information. And that's the whole power of Bayes, is that you can do that and it's all, it works. If you don't do that, if you don't allow yourself to do that, then a lot of times it looks like you're just ruined and you can't make any progress. But of course you do have that previous information. You have those other experiments. You have all that stuff. And you can use that information by expanding the likelihood to include that other information. And what I've found is that it's a very restrictive way to make you force yourself to be very clear about like what measurements were made, what can I really justify based on empirical evidence and things like that. And it's the same information that if I wanted to say, this is an important point that'll come up later again, but we'll just do it now. Let's say that I'm doing this, and you say, here's a prior, and I say I don't like your prior because where did it come from? That's subjective. And you're like, it's not subjective. There was this previous experiment that I did. That's why I know. And I'm like, okay, well, where does that information come from? That pi of mu would really be, let me lift this up. That pi of mu is secretly, pi of mu given some other measurement y, right? And that thing is the likelihood function, p of y given mu times some new, even original prior. I'll call it eta of mu because this is consistent with my notes later. So you can say that your prior is really a posterior, that came from some other measurements. Fine. You got that by using Bayes' theorem, and that there's a likelihood that we can both agree on. And now I'm going to ask you where you got this. And you could say you got it from another measurement. We're just going to keep doing it ad infinitum until we get to a point where you're like, I just made it up, right? So now, if you're in a situation where you can dominate what's going on here, then you don't really care, right? But if you're not in one of those situations, then you still care about where that came from, okay? But what's great is that as a frequentist, I can just identify this term. We both agree on it. It's the likelihood. Both Bayesians and frequentists agree on the likelihood. And I can basically, take p of x given mu and p of y given mu. And if they're independent things, I can just multiply them together. And I can use that information in a frequentist way to do basically the same thing. So what I've found myself is that not allowing myself to put the prior in and forcing myself to go find what that other measurement was and including it in the likelihood function explicitly usually makes me understand what's going on a lot better. So I think it's like time well spent, basically. Okay, so this part maybe I can do kind of quick. We're going to kind of blow through this a little bit. So we've talked about basically at this point just probability and like foundations. But here's the first like in-action statistical thing we might want to do, which is to estimate a quantity. Okay. So here you can imagine like alpha is something like the mass of a particle. Alpha hat as a function of the data is what I'm going to call an estimator generally. Okay, so it's a function that I stick data in. I turn the crank and I get out a number. Okay, because it's a function of the data, alpha hat is random. Right? If I did the experiment again, the data is going to be different. I run it through the same crank. I get out a different alpha hat. Okay. So then what I can talk about is, for instance, the expectation of alpha hat, right? Which is just the average value of it. Okay. If you want, all this expectation language is going to be integral of whatever is here, times the distribution dx, right? Okay. Typical expectation. So then you can talk about properties of estimators. So all of this is abstract. Then we'll talk about specific estimators. So I can talk about the bias of an estimator, which is basically I take the expectation of alpha hat. But this part gets a little tricky, is that the expectation of alpha hat depends on whatever the true value of alpha is, right? If I have a Gaussian like this, if the mean is here, the expectation of the data is here. If the mean's over there, then the expectation of the data is over there. So all these expectations, I've tried to write, the bar given the value that you're assuming to be the true value, okay? And then I subtract off the true value. Okay, so if the expectation is equal to the true value, then it's unbiased, okay? Then you talk about the variance, which is basically, these are all the things you've seen a million times in physics classes and things, right? So it's how much the estimator minus the mean value of the estimator, squared moves around. And then there's also the notion of asymptotic bias and asymptotic variance, which is just like if I have a lot of data in the limit, what happens? So you can have estimators that are biased, but if you get a lot of data, then it becomes unbiased. So let me give a couple quick examples, and then I'll try to blow your mind, and then we'll stop. Okay? So the
value by definition, a lot of different like you go back to one slide.
Oh no. So I could just have one, like if I have a Gaussian, I could just have one observation of x. And then I calculate alpha hat based on that one observation. But this expectation is that you're imagining I repeat the experiment over and over again, and I look at all the alpha hats that I got from all those experiments and take that. Okay, so here's a very quick one. So one specific type of estimator, which is probably the most used one, is called the maximum likelihood estimator. So again, we have our likelihood curve. I made it minus log likelihood, so it's the minimum of that. That's the so and I'm going to use this argmax notation. Okay, just like what value of alpha maximizes that thing. If you have a Poisson, you can do it very easily, right? So I can imagine it has a fixed value of n. I just take the log of that thing. I take the derivative. I set it equal to 0. I get this, and then I solve for mu hat, and it's just equal to n. Okay, it's exactly what you would expect. If I want to know what's my best guess for the average number of whatever car crashes in a year, and there were some number of car crashes this year, that's my best guess, right? So this is very, very straightforward one. Okay, we could also do a Gaussian. Same thing. What's the here I'm going to have repeated measurements. So I'm imagining that it's not just one, but I have like n samples from the Gaussian. Again, you just take the log of it. So your exponent goes down. I take the derivative, set it equal to 0, and the maximum likelihood estimate for the mean is just 1 over n times the sum of all is the sample mean. Okay, super obvious, but it's I'm not saying if I could have just told you that my estimator for the mean is this function, but there's a little it didn't have to be also the maximum likelihood estimator, right? It happens to be. So here's a counterexample where things get a little bit more interesting. If I thought about sigma squared, not sigma, but sigma squared as a parameter of the model, and I wanted the maximum likelihood estimator of sigma squared, you can do the same calculus, and you get 1 over n times x minus the mean squared, blah, blah, blah. And that thing turns out to be biased. The maximum likelihood estimator in this case is biased. Okay. You can do some work and show that 1 over n minus 1 is unbiased. Okay, this is a different estimator. This is not the maximum likelihood estimator, right? I mean, I don't care at all about this 1 over n and 1 over n minus 1 stuff. That's not the point. The point is like conceptually, here's the MLE. Here's an MLE. Does it have this property? No, it's not unbiased. It's biased. Here's something that's unbiased, but I don't. Where did it come from? It's just someone created this function. And it happens to be unbiased. Another thing that's interesting at this point down here is if I wasn't trying to estimate the parameter sigma squared, but the parameter sigma, I could just take the square roots of both of these. They're both biased. You would think that sigma, the estimate of sigma with the square root of this thing would be unbiased, right? But now you have to remember that sigma hat is a random thing with a distribution, and I change variables from sigma squared to sigma. So I pick up a Jacobian factor. So if it was unbiased before, it's going to be biased now because that Jacobian factor is like 1 over x or something. Or 1 over sigma. So there's just trying to simple examples that bring a lot of these things together. Okay.
So to show that you would multiply by the variable and then put the Gaussian in there, integrate over it. And
exactly. That's right. I mean, it's a straightforward calculation. Just kind of becomes a little bit annoying to write down. Okay. So I'm going to skip this is covariance. Covariance, I think people have seen it. One thing that's interesting that I'll mention is that these are example scatter points of two-dimensional data that the different rows all have the same covariance. And what I love is the bottom one. All of these examples are uncorrelated data. Okay? And so basically, whenever things are symmetric, it's going to be uncorrelated. Okay, basically, it's just saying as I move the mean of x, how does the mean of y change? And then it always balances out. So this is all uncorrelated data, but clearly there's dependence, right? So one thing that happens a lot in physics is people use the word correlation in place of the word like some sort of functional dependence or that they're dependent on each other. So there's a better quantity called the mutual information. Here's the formula for it. And this thing has the property that if the distribution of x, the joint distribution of x and y factorizes into a distribution of x times a distribution of y, then the mutual information is 0. Okay, so that's like the thing that you really want. You don't want to talk about correlation. You want to think about, does the distribution factorize? Okay. Now, I know we're kind of at it, but I'm going to have a big ending here. Okay, so so we talked about variance. There's also something called the mean squared error, okay, which is very similar. The difference between the two is that the mean squared error is saying how different is my estimator from the true unknown value, okay, and the variance is how different is my estimator from its average value. Like how much does it move around there? And so the mean squared error you can rewrite as a variance piece plus a bias piece squared, okay. So I think you've probably seen all of this in different contexts, okay, different. But I'm mentioning it for a reason, okay? So here's like the first kind of nice result is that if you want an estimator that's unbiased, okay, physicists tend to be, I think I wrote it on this previous slide, physicists seem to be allergic to the idea of a biased estimator, right? It sounds horrible, it's biased, right? So we always are looking for unbiased estimators. And so this thing that I'm about to show you called the Kramer Rao Bound is very nice. So if among the class of estimators that are unbiased, the variance of them has to be bigger than some quantity. So there's a lower bound on the variance of an estimator. You can't. That means like you can't like constantly have competitions with each other to see if someone can come up with a better estimator. Like there is a bottom floor that you cannot do better than, and it's better than 1 over this I of theta. And I is called the Fisher information, okay? And there you take this is the log likelihood. You take the derivative of the log likelihood respect to the parameter. This is for the case of multiple parameters with respect to I and with respect to j. And then you take the expectation of this quantity, when theta is true, and you get out this quantity, okay? So you can also this is also a statement for the covariance. So if you have a statistical model, you can calculate this thing, and it's just telling you there's no way to do better than that. So there's like a certain amount of information in the data, and you can't squeeze out any more than that, okay? Which is a nice result. And I'll talk about this thing more later, but this has all the properties of a metric tensor, and this equips your theory with a Riemannian metric. So you can think of your theory in a nice geometric way. It has all sorts of nice properties, and we can talk about it later. Okay. So if you have an estimator that hits equality here, then you say it has reached the minimum variance bound. Okay, so that's nice to know. But now here's my ending point to blow your mind, and then we'll stop. Okay, is that let's think of this very, very simple case of a cloud of data. Okay, it's a multivariate Gaussian. Okay, so here's my simple multivariate Gaussian. It'll be the same in all directions and perfectly round. Okay, and it's centered around some point, mu, and all the components mu I are just telling me all the different components of mu. So here's my cloud of points. Okay, so like is some point 3, 5, whatever 3, something like that. And if my goal is to try to minimize the mean squared error, okay, so I want to come up with an estimator that minimizes this thing. Okay, then I could consider 2 different options. One is, I think, the most obvious thing to do. It's a Gaussian, it's perfectly symmetrical. I just take the points and I just take the mean of my points, right? And so that's the maximum likelihood estimator of the mean, and it's just the simple thing, and it's unbiased. Okay. The other thing that I could do is take that same mean vector and shift it towards the origin by some amount. Okay, so n here is the number of dimensions. This mod x bar is like how far out is the mean, right? So it's some weird thing. So if n is bigger than 2, then I'm multiplying it by 1 minus some number. So it's moving it towards the origin. Okay, it is clearly biased because if the first one wasn't biased and I'm systematically moving it towards the origin, this one's clearly biased. Okay, so this is weird, right? It's a weird thing. And as a physicist, this should bother you, right? Like, what makes 0, 0, 0 special, right? It clearly doesn't obey. Like, this estimator is not translationally invariant, right? That's a problem, So, but it looks bad for lots of reasons. But this James-Stein estimator has a lot smaller mean squared error than the maximum likelihood estimator does. So if what you mean by a good estimator is that it's close to the truth, then it's better by a lot, right? But so what's going on, right? This is me blowing your mind. Hopefully I'm blowing your mind at least a little bit. So this thing is doing better And in fact, it always does better. So there's this term dominates. Okay, but so what's happening is that the mean squared error has two parts to it. It has a variance piece and a bias piece. And you know from the Kramer Rao Bound that the maximum likelihood estimator is basically only it says like the penalty for being biased is infinite, right? I can't let you be biased at all. And so then I just do the best I can with the variance, right? But if I don't put an infinity coefficient in front of here and I just put them even weight of like how bad is it to be biased versus have some variance, then the maximum likelihood estimator is not optimizing this thing, and the James Stein estimator is. So it's and then the kind of the somewhat intuitive picture of what's going on is that in high dimensions, all the volume is out on this, away from the, if this is the origin, all the volume's on the shells out there, right? So it's sort of taking all the points and pushing the volume out there, and by shrinking towards the middle, you're taking that cloud of points and you're biasing it, but you're shrinking the volume down by a lot. And in high dimensions, that's a really big effect. So this plot that I showed was how big the mean squared error is as a function of the dimensionality. So if you're in 20 dimensions or something, it's a huge difference. And but it works for 3 or more dimensions. So, anyways, so that example, which I'm not going to get into now, was then to set up the statistical decision theory stuff a little bit, because now you see, like, what is my goal, right? I have to state my goal. Do I want, I have this notion of bias, I have this notion of variance. How much do I care about those two? You need to tell me what your goal is. And that's going to be this one ingredient called the loss function in this language. And once you do that, then we have a framework to talk about how to proceed and what's the best way forward. And then you'll also see that certain of these quantities that we can talk about will require a prior and other ones won't. Okay, but we'll get to that later. Okay. All right, thank you. Yeah.
Regarding parameter estimation.
And what significant figures you said? Okay.
Most people say that your data is only accurate so many decimal places, etc. Therefore, your estimate of your parameters is only so accurate.
Right.
But for parameter estimation, you now have a real number.
Right.
Has principally nothing to do with any significant figures.
That's right.
So, in the case we have asymptotically